Today we are going to talk about vectors in our notes, and this is your first set of notes in playlist 2. So again, please jot these things down. Starting with our definition. A vector is a quantity with magnitude and direction. We've actually already talked about several vectors in this class, and I've even used that word in talking about some of these things. But things like acceleration, displacement, velocity, these are vector quantities. And what it means to be a vector is that it has both a number value, for example, velocity, how fast it's going, you could say, 20 meters per second, okay, a number value and a direction, okay, so 20 meters per second downward, for example. And that makes it a vector quantity. Now, because it is a quantity with both a magnitude and a direction, we can represent vectors with an arrow, because arrows also can represent magnitudes. How long the arrow is can show how large the value is, and direction, because arrows, of course, point a certain way. And so whenever we represent our vectors with arrows, the arrow length can show the quantity or the magnitude of the value. Longer arrows will represent larger quantities. Shorter arrows will represent smaller quantities. And then the arrowhead can show the direction. And so we can represent these vector quantities like velocity, acceleration, and displacement with arrows. And that's what we're going to look at today, is how we can represent these with arrows, and then how we can use those to determine what our resultant velocity, or really it's just velocity for right now, or displacement, I guess, would be if we have those arrows pointing in more than one direction. Okay, and so we'll get to that later on. But again, you need to start with the definition. A vector is a quantity with magnitude and direction. Okay, so we're going to do an example of a vector diagram. And so in this, and you might want to draw this on your page, I have a ball shown at 3 different positions, time of 0, time of 1 second, and time of 2 seconds. And the question says, or the example says, a ball is thrown upward in the air. Its position is shown at release, at 1 second, and at 2 seconds. Assume there is no air resistance and that the ball reaches max height at 3 seconds. Diagram velocity and acceleration vectors for each position. Okay, so we're going to start with the velocity vectors. So initially, this ball is thrown upward. So it has an initial upward velocity. We don't have any numbers, that's okay. I'm just going to draw an upward pointing arrow like this at that first ball down there for t equals 0 seconds. Okay, I'm going to color code mine, so my velocity vectors are going to be yellow and my acceleration vectors will be red. But if you don't have different colors, you might want to just label it and say this is V, put a V next to it. Okay, so that's my initial velocity, or my velocity at time 0. What is my velocity going to look like after 1 second? What's going to happen to my velocity? Is it going to be the same? No, it's going to be slower, right? Because this thing is being thrown upward, and we know that it's going to slow down as it rises. And so the next arrow I draw still points up, but is shorter. Okay, that shows that it has less magnitude. That shows that it's slower, but it's still going upward. And I know it's still going upward because the question says it reaches max height at 3 seconds, which means it's going to go upward until 3 seconds, and then it's going to stop and fall back down. Okay, but I don't even have to worry about 3 seconds. It's not on my screen. Okay, so at 1 second, it's a little shorter. What about at 2 seconds? Is it going to be the same length as this one? Nope, still going to be shorter. Okay, still pointing up. Something like this. I don't have numbers to associate with this. That's fine. Just draw them so that the one at the bottom is longest and they get shorter as you go up, and you'll be good. It's just a relative depiction of the amount of, or the magnitude of the velocity. So the arrow should get shorter as it's slower. Now, could you draw it perfectly to scale if you had calculated it? Yes, you could. And if you really want to, you're welcome to pull out a ruler and draw it to scale. And that is perfectly fine if you want to do that. In fact, whenever we start doing some of these things, if you draw everything perfectly to scale, you can actually solve it that way instead of doing it mathematically. But personally, I think it takes way too much time to do that. So, but this would be how you represent your velocities. Okay, now we're going to do the same thing for acceleration. Guys, the velocity is changing here, which means I have acceleration. What is causing my acceleration? Why is my velocity getting slower? Gravity. Is the value for acceleration due to gravity going to change at these positions? No. Acceleration due to gravity is always the same. It specifically is going to be negative 10, or if you want more specifically, negative 9.8, but it's downward. Okay, and so here's my acceleration vector for this position. It's a downward pointing arrow, and at this next position, it's going to be the exact same length because it's the same acceleration. It's still negative 10. And at the third one, it's still negative 10. It's negative 10 at every position in the trajectory. And so all of my acceleration vectors are going to be the same length, and they are all pointing downward because acceleration is downward toward the surface of the earth whenever we're talking about acceleration due to gravity. Okay, so this is how you can represent vectors for a specific scenario like this. Okay, and this is two different types of vectors. We have an acceleration vector and a velocity vector. If we have the same type of vector, we could add them together, and we could practice vector addition. But you can't do that with the previous example. But we'll do one with this stuff. Okay, so vector addition. We can add two vectors of the same type together for a visual representation of the mathematical process. So if you have two velocities, and I'll give you an example in a second. In fact, here's one right here. If you're on that moving sidewalk at the airport, you know what I'm talking about? It's like an escalator, but it's flat, and it moves, and you can just stand on it, and it'll get you there. Or you can walk on it and go even faster. Okay, well, that's what this is talking about. The moving sidewalk at the airport travels 2 meters per second forward. If you walk forward at 3 meters per second while on this surface, what is your velocity relative to a stationary observer? So if the sidewalk's already moving and now you're moving on it, you can figure out how fast you'd be going, but you're going to add the two together. Okay, and you can add the two numbers together from the question, or you can add the two vectors together if you draw them. So this vector is going to represent the 2 meters per second that the sidewalk is moving. And if I want to add another vector to it, here's my 3 meters per second that I'm moving. You're going to add them using something called the head to tail method, or the tip to tail method, where you add them so that where your first arrow ends, the head of the first arrow is going to be where the tail of the next arrow starts. It's head to tail, okay, or tip to tail. So the tip of this arrow touches the tail of this arrow. Okay, and we can add these together, and when we add them together, we're going to get 5. Okay, but the solution is called a resultant vector. It is drawn from the tail of the first vector to the head of the last one, from where you started to where you ended, and here it's represented by this green arrow. Okay, now regardless of whether you added these with the numbers in the question, or maybe you drew this to scale and you added them here where you had it labeled 2 and 3, you're still going to get 5 either way. Okay, sometimes it is easier to see whenever we're adding the vectors if we draw them, and sometimes it's not necessary. In this particular question, I would say you don't necessarily have to draw that to be able to understand what you're doing, but it doesn't hurt anything to do it, and either way you're going to get 5 meters per second. Okay, so this is vector addition. When we add vectors, we add them head to tail, just like this example. And we call the answer the resultant vector. The resultant vector is drawn from the starting point of the first arrow to the head of the last arrow, or from the tail to the tip, whenever you're adding them together. All right, so here is another one. This one says, add the following displacement vectors that represent the path a student took through the hallways at BHS. And I have 4 vectors here, A, B, C, and D, and we're going to add them together. This will be easier with some grid paper. We don't have that on my screen, so we're just going to add them. And so I'm going to start with A, and then I'm going to add B, again, head to tail, and then I'm going to add C. Now this is a little bit different because A and B are in the same direction, but C is diagonal, but same rules, head to tail. And then D, head to tail. Okay, when you do this, if I asked you, hey, what is my final displacement, you could represent that answer with a resultant vector that looks like this. Okay, now if I had drawn this on, graph paper and had drawn it to scale, could I measure that? Absolutely. Okay, right now it doesn't really mean much, but you could. Okay, or maybe you could calculate it if you had some angles in there, which we're going to be bringing in later on. Okay, however, there's more than one way to draw this and still get this exact same resultant vector. The order of addition does not matter. You could add them like this. Here's the green one, and then the yellow one, and then the red one, and then the pink one, and this is the exact same resultant vector. It has the same magnitude, and it has the same direction. Okay, so the order does not matter. You can add them in any order. So again, vector addition, all we're doing here is practicing head to tail whenever you add. All right, so if I give you an initial velocity and a final velocity in a vector diagram, you would have to use vector addition to solve for acceleration. We're going to talk about finding acceleration by vector addition. Okay, what if I gave you vectors instead of numbers? Okay. So remember, the equation for acceleration is your change in velocity divided by time. So v minus v naught over t. Well, it's called vector addition, not vector subtraction. And so we need to rewrite this so that we are adding, because it only works by addition. V minus v naught could be rewritten as v plus negative v naught. Everybody agree with that? Over t. Okay, and so we can do this. Now, in physics, the negative signs on our numbers tell us direction. Okay, and so if I have a negative vector, I just need to change the direction from the positive to the negative direction. This is what v naught looks like according to this example. If I want to show what negative v naught looks like, I simply flip the arrow around and draw it in the exact opposite direction. That would be negative v naught. Okay, because v naught was like, let me go back real quick. V naught was here, negative v naught looks like that. Now I can add them. V plus negative v naught. And so if I want to add them, here's my vector for my final velocity, here's my vector for my initial velocity, and my resultant would represent the answer or the change in velocity between the two would be that right there. Again, if it was in vector form, I would use that. That would be my change in velocity. I could find my acceleration if I had a value to go with this, or if I was measuring it or something, and then I could divide it by my time to get acceleration. This is going to make more sense when we use some actual numbers with it. Okay, but for now I just want you to see how you line them up. It's still head to tail, but if you have something where you're trying to subtract, you just add the negative. So flip the arrow around and add it on. All right, so here's where we're going with this. Okay, so far we've talked about basically one-dimensional motion only. We've had objects that are moving at constant velocity in one direction, or maybe they go forward and then backward. Or we have objects accelerating, or we have objects that we throw up in the air straight up and they come straight back down, or we drop them from rest. But everything has been in one dimension. When we start talking about projectile motion, now we're going to be looking at some scenarios where we have motion in two dimensions. Because in this particular image, for example, the ball that this boy throws at any given point is moving both forward and up or down, depending on which point we choose. And so it has motion in two different directions, and those velocities, which are vectors, can be added together in the way that I just showed you. Okay, so let's go ahead and take a look at this. Projectile motion is a form of motion experienced by an object or particle that is projected near Earth's surface and moves along a curved path under the action of gravity only. Technically, these objects in projectile motion are still in free fall. Okay, after they have been launched or thrown or whatever, they are now in free fall, and the only force acting on them is gravity. Thus, we will be using two-dimensional vector addition as we analyze simultaneous horizontal and vertical motion of an object at the same point. So if I pick a point, okay, like this one, we can look at both the horizontal and vertical motion at that specific point. So at this point, the ball is moving forward or to the right, but it's also moving down. Do you guys agree? Okay, and so we could represent our velocities like this. We have some amount of velocity in the x direction, or horizontal velocity, and we have some amount of velocity in the y direction, or vertically. Okay, forward and down at the same time. Okay, if we add them together, like we just did with our vector addition, we can figure out what the total velocity would be. Okay, but when we do all of our calculations later on, you're going to be calculating horizontal and vertical separately, finding those two pieces and then adding them together to get your resultant. Okay, so what is the speed? At the point circled, use vector addition and add these head to tail to find the resultant vector. Again, you could add them head to tail like this, or you could have moved Vy at the end of Vx. It doesn't matter. It doesn't matter what order you add them in. Either way, here's my two vectors added together, head to tail. Here is my resultant. So if I asked you to find the speed at that position, I would be asking for this total speed. I don't want just the vertical. I don't want just the horizontal. I want the total, the resultant. Okay, and whenever you draw this, you have just formed a right triangle. So how could I find this piece? I heard somebody whisper it. Pythagorean theorem. This is the hypotenuse of a right triangle, and you can solve for it using Pythagorean theorem. So yes, we're going to bring in some geometry. We're also going to bring in trig once we start putting angles in, sine, cosine, and tangent. So get ready. All right. So you can solve for this with Pythagorean theorem. Okay, so if we add together our two components of our velocity, our horizontal component and our vertical component, we get this resultant, and we can solve for it with Pythagorean theorem if we know the two components. So here's an example, and I gave you a really easy one. Okay, what would my resultant velocity be in this example? If my vertical is 3 and my horizontal is 4. Yeah, it's a 3, 4, 5 right triangle. But let's go ahead and solve for it. A squared plus b squared equals v squared this time. So that's going to be 9 plus 16, which is 25, equals v squared. And of course, I want just v, so square root, and you get 5. So the resultant velocity would be 5 meters per second. I would need a direction as well for it to be a velocity, but the question actually only asks for speed, so that's okay. This is acceptable because that is the magnitude of my velocity. That is my speed at that point, would be 5 meters per second based on those numbers. Does anybody have a question about this? Okay. We're going to get more into that later, as I mentioned, but for now, that is the end of our vector notes. And so for the rest of the class period today, you can work on playlist 1, which is due tonight by 11:59 p.m. That is 202, 203, and 204, as well as your checkpoint 205. You also could start, if you're done with all of this, you're welcome to start looking at playlist 2 because today's notes started that. Or your bump assignment or whatever else. If you have any questions as you're working, please let me know.